Okay, let's go ahead and get started. So today we're going to continue talking about elementary proofs, and in particular, we're going to start with biconditional statements. So recall, wait for my camera to adjust, okay? So recall the biconditional statement, P if and only if Q, okay? So this, if you've followed through the textbook, is logically equivalent to P implies Q and Q implies P. Okay, so when encountering mathematical statements that are biconditional, so you have P implies Q, Q implies P, this is equivalent to proving P implies Q and Q implies P. Okay, so let's look at an example. So claim. So an integer n is even, okay, if and only if n squared is even. Okay, so an integer n is even if and only if n squared is even. So this is a biconditional statement. Okay, we have two things to prove if we're going to prove this claim. The first being, so the first direction would be if n is even, then n squared is even. Okay? And two, if n squared is even, then n is even. So in order to prove this claim, since it's a biconditional, it is if and only if, biconditional, we have two things to prove. Okay? We have the conditional and the converse of the conditional. So these types of proofs are a little bit longer because you have two different things to prove. Okay? So I'm probably going to run out of room if I do my scratch work. So I will leave it to you to do the scratch work on your own, but let's go ahead and prove this without scratch work. Okay? So, proof. Now again, I can't emphasize this enough. Even though I'm doing it without scratch work, you need to have on the side of your paper scratch work that you can work these things out before you try to write the formal proof down. Okay, so I'm going to prove part one first. Okay, if n is even, then n squared is even. So, so let's say we're just going to use a direct proof in the first one. So let n be even. Okay, so this is a direct proof, so we just assume the hypothesis, n is even. Okay, then as before, after we make our assumption, we're going to recall a definition. So we can say, then, by definition, there exists an integer k such that n is equal to 2 times k. Okay? So we assume the hypothesis of part 1, we recall the definition, and then we're going to do a little bit of algebra to show that the conclusion is true. So we can say something like, hence, n squared is equal to 2k squared, which is equal to 4k squared, which is equal to 2 times 2k squared. Okay? Since 2k squared is an integer, we have shown n squared to be twice an integer, so n squared is even by definition. So that proves part 1 of this biconditional statement. So next we have to prove the converse of that conditional. If n squared is even, then n is even. So we start that by starting a new paragraph and say conversely, okay, conversely, we need to prove this, and then we give the proof of the second part. Now, if you've been keeping up with the homework, you will notice that this type of proof, if n squared is even and n is even, can be done by non-direct methods. That's probably the best way to do it. So I'm going to do that by proving the contrapositive of part 2. So the contrapositive of part 2, so you negate the conclusion and you prove that that implies the negation of the hypothesis. So this would be n is odd, then n squared is odd. These are equivalent statements because this is the contrapositive of part 2. So if we prove this, we prove part 2. And that's what we're going to do. So we're going to say conversely, and by way of contraposition, because remember, when you do a non-direct proof, you need to tell the reader that you're doing so. Position, by way of contraposition. Assume n is odd. Okay. And so we've made an assumption now, so now we're going to recall a definition. So we're going to say, then, by definition, there exists an integer k such that n is equal to 2 times k plus 1. That's the definition of being odd, right? Hence, so actually here, normally I would write just like this. Equation followed down by equations. I would do that right here. But I'm going to run out of room. So I'm just going to do one line here. But on your paper, you should always make room to do it like this, for me. Okay? But I'm just going to write it in one line so I can fit it in here. So hence, n squared is equal to 2k plus 1 all squared, which is equal to 4k squared plus 4k plus 1. Okay? And now we need to make this look odd. It doesn't look odd right now, but we can do that by factoring out a 2 in here. 2 times k, 2 times 2k squared plus 2k plus 1. Now all of this right here should have been done like this. Okay, I can't emphasize that enough. It should have been straight down. I'm just running out of room. Okay, so we've established that n squared is equal to twice this plus 1. Since this is an integer, n squared satisfies the definition of being odd. So we can just say, since 2k squared plus 2k is an integer, n squared is odd by definition. And then we're done. We've proven that, which is the same thing as proving part 2. So we've proven the if and only if, the biconditional claim that we made. Okay? So biconditional statements will come up in your mathematics courses, and you have to always remember to prove both things. I can't emphasize this enough because I'll see math majors make it to their junior, senior courses and see a biconditional statement and prove one direction and just completely forget about proving the other direction. Okay? So take a moment to jot that down. Okay. So let's go ahead and do another proof. Let's do another biconditional proof. So maybe we'll do something like five and six. So name. So just say n is odd if and only if. If you ever see a mathematician write IFF, this is if and only if. It's the biconditional statement. If and only if 5n plus 6 is odd. That's a 5. Okay? So n is odd if and only if 5n plus 6 is odd. Okay? So there's two directions to prove here. It's a biconditional statement. So the first direction is going to be assuming n is odd, and that implies 5n plus 6 is odd. The second direction is 5n plus 6 is odd, implies n is odd. And we're not going to talk about this terminology today, but we will. This is proving a necessity and sufficiency of a claim. But we'll get into that later in the semester. I'm just trying to introduce you to the concept of biconditional proofs. So again, you should use scratch work on your own. I'm not going to because I have a small board, but let's go ahead and prove this. So we're going to start off by assuming n is odd and showing 5n plus 6 is odd. So let n be odd. Okay, so we're assuming if n is odd, then we need to show 5n plus 6 is odd. So let n be odd. As you can guess what we're going to do next, by definition, there exists an integer k so that n is equal to 2 times k plus 1. Okay, now that we've used our definition, we have information about n, and we should look at the conclusion 5n plus 6 now. Again, recall we're trying to prove if n is odd, then 5n plus 6 is odd first. So then, um, 5n plus 6 is equal to 5 times 2k plus 1 plus 6. Okay, and this is equal to 10k plus 5 plus 6. Okay, and our goal here is to make this look odd. So one way we can do that is we're going to leave off a 1 at the end here, and we're going to group together the rest of the values. So we'll have 10k plus 10 plus 1. So notice 5 plus 6, right, is 11, which is the same thing as 10 plus 1. But now, because I've grouped the numbers this way, I see there's a common factor of 2 between those numbers there, right, between these parts of the equation. So then we see that this is equal to 2 times 5k plus 2 plus 1. Now that looks odd, 2 times an integer plus 1. So now we just need to say that. So since 5k plus 2, oh, wait a minute. That should be a 5. Okay. Since 5k plus 5 is an integer, 5n plus 6 is odd by definition. So this has proven the first part of this claim. Okay? So now we need to show if 5n plus 6 is odd, then n is odd. Now already looking at it, if I assume directly that 5n plus 6 is odd, I'm going to get 5n plus 6 is equal to 2k plus 1, and I got to solve for n. If I had scratch work going, I would see that that wouldn't be the way to go. So we needed to use an indirect proof. I.e., we need to show the contrapositive of 5n plus 6 is odd, then n is odd to be true. That's one way to do it. So the contrapositive of that statement is, if n is even, then 5n plus 6 is even. So start a new paragraph. So conversely, and by way of contraposition, suppose n is even. Okay? So then once you have your assumption, your supposition, you can say the definition, right? By definition, there exists an integer k, so that n is equal to 2 times k. Yeah? So then we need to show that that implies 5n plus 6 is even. Because again, I can't emphasize this enough. We're proving the positive of 5n plus 6 is odd implies n is odd. So we assume that n is even, and we have to show that 5n plus 6. So we can say then 5n plus 6 is equal to 5 times 2k plus 6. And we want to show this is even. I see there's a factor of 2 here and a factor of 2 there. Take that out. So this is equal to 2 times 5k plus 3. 2 times 5k plus 3. Okay? So now we just have to state the definition. Since 5k plus 3 is an integer, 5n plus 6 is odd by definition. And then we're done. That proves necessity and sufficiency of that claim. Okay? So again, notice that there's two different proofs we have to do. We have to prove if that, then that, and then if that, then that. Okay. Okay, let me see if I can find another good one to do real fast. Actually, I think that that does it really for the biconditionals. Those are two pretty good examples for you to look at. So next, let's look at maybe proof by cases. Okay. So proof by cases is just a way of exhausting the possibilities of a claim. So claim. The claim is if n is even, no, sorry. So if n is an integer, okay, then n times n plus 1 is even. Okay? So if n is an integer, then n times n plus 1 is even. Okay? Maybe get it in focus there. There it goes. So how would we prove this? Well, there's two cases to do this. Microphone. So if n is an integer, then it's either even or odd, right? So those are the only two possibilities for the properties of n. So what we're going to do is we're going to check when n is even and then show that this must be even, right? And then we're going to assume n is odd and then show that this also must be even. That exhausts both possible cases for n, and then that would prove that if in both those cases this is even, that would prove the claim. So let's look at what that would look like. So proof okay. So we're going to say let n, let's go ahead and use the same notation, so let n be an integer. Okay? So we're assuming the hypothesis, it's a direct proof. And then we're going to say since every integer is either even or odd, we proceed we only need to consider the following two cases. Since every integer is either even or odd, we only need to consider the following two cases. The cases where n is the case when n is even, the cases when n is odd. So case 1. Oh, so number 1. The case 1, n is even. Okay? So we have an assumption now on n, it's even, so we can use the definition. So then, by definition, there exists an integer k so that n is equal to 2 times k. Okay? So now we need to consider the hypothesis. Then, n times n plus 1 is equal to, well, I'm not going to change anything about that in there. I'm just going to I'm going to change the first n. And you'll see why in a second. I don't need to even look at the other one. So n times n plus 1 is equal to 2k times n plus 1, but this is equal to 2 times k times n plus k. Just send in the k. So now, since kn plus k is an integer, n times n plus 1 is even. So if n is even, then n times n plus 1 is even. Okay? So now we need to consider the case when n is odd. So case 2. By the way, sometimes when people prove these cases, they'll put like a little QED box and then parentheses around it to show that they've finished the proof of the case. And so case 2 is that n is odd. So now we have to consider that case. So then, by definition, there exists an integer k so that, by the way, if you're writing this on your paper, there should be a distinct line, like a white space line between case 1 and case 2. Okay, so go back to this, n is odd, so n is equal to 2 times k plus 1. Okay? So then, we need to consider the conclusion again. So n times n plus 1. I'm going to leave that n alone, and now I'm going to change the n in here, and you'll see why in a second. This is equal to n times 2k plus 1 for that n. Doesn't look like you can see that because of the glare. So maybe because of the glare, I'll write it like over here so you can see it, but technically it should be right here. So, okay, n times n plus 1 is equal to n times 2k plus 1 plus 1. And so that n was replaced by that 2k plus 1. And then we get that this is equal to n times 2k plus 2. And then we see that there's a factor of 2 here. We can factor that out. We can send the n back in there. So then we get 2 times n times k plus n. Okay, so that technically should have been right here. Okay? Since n times k plus n is an integer, n times n plus 1 is even by definition. Okay, so We just need to state that we've finished now. So we've proven case 1, we've proven case 2. There's a little baby QED to show that we've proven the cases. So then we finally say the last sentence outside of the cases would be something like, in both cases, the claim holds and our proof is done. And then big QED. So in both cases, our proof is done. Okay, so that's an example of proof by cases. Let's see if there's any more that I want to do today. Actually, I think that'll be it for today. So you've seen biconditional proofs today, and you've seen proof by cases. We have to exhaust the possibilities. All of these should be in your textbook, by the way, like these types of things. So for those of you that are also in my discrete math class, we're going to start separating more. Discrete math and intro to proofs are very similar, but right around here, we're going to start separating a bit. So if you become accustomed to watching just one channel, one YouTube channel's videos, you're going to have to start watching both soon. Okay, so that'll be it for today. We will meet again on Thursday. Okay, so y'all stay safe, stay dry, and I'll see you Thursday. Have a good day.